see how the step size will affect the acceptance rate of numerical integrator and leapfrog. If you haven't done that, you can try to use the new version and see how it's going on. But if you haven't done that, you want to see like if I reduce the size of the step size, what will happen? You can do that as well. Both either is fine. Okay, any question regarding homework? Okay, great. So let us continue with the generative adversarial networks. In last lecture, we introduced the goal of the GANs, right? And also the key idea to train the GANs, right? So first, what is the goal of the generative adversarial networks? What's the goal? Really speaking, we shouldn't say we want to estimate distribution. Instead, we want to estimate a transformation. A transformation which can transform an easy distribution samples into an arbitrary complicated distribution samples. And those complicated distributions are reflected by a set of training data, right? So like a set of cat images or a set of drawings from Picasso, right? And then I just want to through any like noise samples, like from Gaussian white noise or from uniform distribution, and I want I through my fabulous transformer, and the output of my transformer will be seen as some examples generated from the same distribution, underlying distribution, like another Picasso's work or another cat. Right? That's the goal for generative adversarial networks. So the key idea to train, again, I mean, this is something really novel here. It's different from a traditional way. Traditional way is either to like maximize likelihood of your model, right, or to minimize some kind of loss. But the training of the generative adversarial networks is to use some gaming mechanism. Right? So we introduced two neural networks. The first network is called generator or faker. So this is something we want, right? We want some action faker such that I can transform any garbage information into a sample. Looks like a new sample coming from the desired distribution, right? But to get this faker, we also introduce a discriminator, right? A police network, and the police network is used to discriminate the samples generated by the faker and the samples coming from the true distribution, the desired distribution, like Picasso's, like Picasso's drawings, or like cats or dogs, whatever. Right? So their training is kind of adversarial. Like the generator tries to improve the quality of its faked examples, and the discriminator tries to makes the best effort to discriminate, to classify the fake examples and the true examples. So they're both like enhancing themselves until they're arriving at some like stationary point, at some balancing point. So that's the idea. So the generator network or the fakers network will receive the noisy examples, the samples generated from arbitrary easy distribution like uniform or Gaussian distribution as the input. The output will be the transform sample. We expect the output of the faker network will look like some samples generated from some desired distribution. Right? And the discriminator or the police network will use the candidate sample as input. So this candidate sample can come from output of the faker's network, or come from some true example generated from desired distribution. The output will be a probability, whether this example really belongs to really comes from this desired distribution or not. So basically, you can view the discriminator of the police network as a classifier. The larger the output probability, the more likely the police think the input candidate example comes from the true distribution, comes from the desired distribution. So the objective function for training, again, is a minimax objective function. It's not to maximize it. It's not to minimize it. It actually finds a saddle point. It's a minimax optimization. So W1 parameterizes the generator's parameters, the faker's parameters, and W2 parameterizes the police network's parameters. Right? So to view the meaning of this objective function, we can look at W1, W2 one by one. So first we can look at when we fix W1, meaning that we have like a fixed faker network, and how what does the police network to maximize this objective mean? Right? So police network maximize the term, the objective term that the police network wants to maximize consists of two expectation terms. Right? So the first expectation is log output probability of the police network under the input comes from the empirical distribution from the training examples. That means as long as the input, the candidate sample comes from the desired distribution, I want the output probability of police network to be as large as possible. Basically, that means I want that if the example is true, it's positive examples, then I want the probability, the output probability to be as large as possible. Ideally, it should be 1. Right? At the same time, we want to maximize another expectation, which is log 1 minus the output probability of the police network, given the input comes from the faker's network. So you maximize 1 minus log probability is equivalent to minimizing the log probability itself, right? So basically, it means that I want to minimize the output probability for any examples generated by the faker's network. So you can view the faker's network's products, the samples generated by faker's networks as a negative examples. Right? So the second term aims to minimize the output probability for the faker's samples, for the samples generated by the faker's network. Right? So you can say, okay, we have like two terms. First, we want to maximize the output probability for the real samples, for the true samples, positive samples, right? And second, I want to minimize the probability for the negative samples. It's very reasonable. It's a typical classifier, typical objective for the classifier. But at the same time, we also want to minimize this whole objective in terms of the faker's network. Right? So if we fix the police network, W2 is fixed, right? Now we want to adjust the faker's network to minimize this objective. What does that mean? So first, the first expectation term has nothing to do with faker's network because it's just parameterized by generator's network weights, right? It only minimizes the second part. So you can imagine W2. The police network is fixed, right? So when I want to minimize this term in terms of W1, I minimize this log 1 minus probability. Essentially, I want to maximize the log output probability of the police network. That means I want to adjust the faker's network structure such that my fake example to be considered by this police network as a true example as much as possible. So when you have some fakes the police network, I'm going to try my best to fake my examples, essentially. To fake my examples such that my goal is that I want to cheat the police network, make it believe that my fake example is a true example. So now you can see the gaming procedure is competing with each other, right? On one hand, the police network tries its best to assign low probability for the fake example. At the same time, the faker's network tries to enhance the probability to be the true example. Right? They're competing with each other. So it's a gaming procedure. And the optimization now is Minimax procedure. And we are essentially finding out the saddle points. Saddle points of the solution. Any questions so far? Okay. So, so given the training problem formulation, which is Minimax problem, right? And in practice, how do we optimize this objective, right? So we usually use a very simple algorithm called Minimax stochastic optimization. So basically, it's just an extension of the normal stochastic gradient descent or stochastic ascent, stochastic gradient ascent, right? So basically, in each iteration, we're going to alternatively update the police network and the fakers network. That's it. So when we update the police network, I'm going to fix the fakers network. Then I'm going to maximize the objective, right? Because it's min-max, right? I'm going to maximize the objective, and then I use the reparameterization trait. Remember, these are expectations. These are expecting, right? So we can sample x and sample z, and to calculate the stochastic gradient, right? And then we can just update the parameters of W2 according to its stochastic gradient. And because we're doing fixed W1, we're doing maximization, right? So actually we're doing stochastic gradient ascent, not stochastic gradient descent. That's why here we should use a plus rather than minus. And gamma TK is just a step size. You can use whatever learning rate schedule to do that. And usually, like we allow, the flexibility allow like key steps to update the police network. And in the original GAN paper, it just said k equals to 1. But in practice, it's tunable. You can choose like I continuously run key steps of the stochastic gradient ascent to update the police network, given the fakers network fixed. And then we update to the fakers network, given the police network fixed. That means I fix W2, then my goal is to minimize this objective, right? If my W2 is fixed, then my goal is just to minimize this objective. Then we just compute the stochastic gradient, then apply the stochastic gradient descent. So you can see they're doing minimax, right? So I just alternative, I fix one part and doing the corresponding maximization or minimization using stochastic update. And then I fix the other part and do the same thing. And then we go to the next iteration and do many iterations until some kind of stopping criterion is arrived, and then we just return the fakers network and the police network.
Is there a reason why the police network is updated first?
No, there's no reason. You can switch them. You can even put this full inside the updating for the fakers network. It's totally up to you. Okay. Yeah. Any question? Okay, looks like it's really straightforward, right? The idea is kind of interesting. It's really interesting, and but the solution is quite straightforward. But actually, there are many variants of those training algorithms. Actually, the original generative adversarial networks has many issues. Like Minimax is not very easy to optimize. So because when you apply any optimization algorithm, it's very easy to arrive some local maximum or local minimum and just stay there. But Minimax, what does it mean? Minimax, just something like this. It's not local maximum, it's not local minimum, but the stationary point is still has the gradient to be 0. But you can see, from this point, you can see it's very easy to move away, right? It's either move along this way or move along this way. So unless like your surface of your curve is very flat at the stationary point, otherwise it's very easy to slip away. So it's actually it's not very easy to train this. So later on, people have developed like numerous variants of the training method for GANs. Like I think the most recent and very influential method is called WGAN, based on word sustained distance. That's very interesting, but it's all about scope. It's very interesting. I think given what we have discussed so far, it's very straightforward for you to look at other versions of GANs. Any question? Okay, so here is just a figure copied from the original paper. So just some illustration of the training procedure, right? So this should use this red marker. This blue line represents the density of the transformed samples, the output of your figures network. And the green line, the blue line are the classifier, which is the police network. Right? And those black dots just represent the training data. So you can see that we do not know the ground truth distribution. We only have seen a set of discrete examples, right? And now this is my initial the density of the initial. The density of the output for the initial figures network, and this is the original. This is the initial police network. So you can see for most examples, most training examples, in the high density region, you have assigned the police network assigned high probability. Right? But for most examples, in a high density region from the figures network, the probability is very low. So you can see the discriminator can well discriminate the examples from the true distribution and the examples generated from figures network. Okay? And then we're gonna doing this minimax optimization. You will see that the training procedure will the figures network will be stimulated by the results of the police network and push the density of its output toward the true distribution. Right? At the same time, the police network is also adjusting its output. And finally, you can see here, this green curve is kind of approaching the true density, right? And finally, they overlap. And then for all the examples, any examples generated from the figures network or generated from the true example, they are assigned the same output probability, but the same output probability could be hurting. It's not that high. So just an illustration of the training procedure to give you a conceptual view of those model training. Any question?
So this is kind of like as t in the previous slide, the algorithm as like t increases.
Yes. Yes. And this will be like some convergence. As some time point will converge. Okay. So here are just a few examples which I copied from Yan Zhu Fellow's original paper. So those are MNIST data set you have done. You have started to do the homework. You know where it comes from, right? So MNIST data are just a set of handwritten digits. So those digits bounded by yellow box are generated by GAN. So you can see it looks like, it really looks like it's come from the same distribution from the training example, right? But they are not exactly the same. That's something interesting, right? I want to fix some example, but I do not want to randomly pick up the existing example. I want to have some variation, but I think this variation does not affect this problem. And the similar examples come from this phase, right? So this new phases are generated by training again over this set of training phases, and those phases are different from any training phase images. It's kind of new phase versus valid phase, right? And similarly, I don't know what it is. Okay, it's kind of some pictures of work. Yeah, some kind of. Oh, sorry. Maybe the resolution is too low. Yeah, some kind of animals or whatever. Yeah, and this one's called style transfer. Right? So this is the original image, and from training, say if you train your GAN with a collection of Picasso's works, now you give any ordinary image, it will transform into another new image which looks like a work by Picasso.
Can you go back to the slides with the GAN training chart? Yeah. So what is the last slide that you just showed? Not this one. The one with the 4 charts. 71.
Mm-hmm.
Yeah. So what is the last image doing? Is that basically defeating the police right there?
Yeah, you can consider as defeating the police.
Okay, so how's that equilibrium though?
It just means the police network consider any examples either from training data or from the output of the figures network as the true example from desired distribution. But this probability might not be 1. It might be like 0.6 or 0.7.
So that is what we want?
Yeah, that's what we want. Because we want to push my figures network output, the density of the figures output, to be aligned with the training example, right? Any other question?
On the next slide, with the digits, so let's say I've like trained my GAN, I give it some random input, and it will produce a random handwritten digit.
Yes.
Okay.
That's our goal, actually.
Okay.
Yeah. I want to I give you any random noise. You can generate another nice looking handwritten digit. But it's not totally not exactly the same as any training digit.
Gotcha. But is it possible if I wanted to generate like a new 0 as opposed to like a new of any digit? Does that make sense? Like, is there some input we can give the GAN to like ensure that we get like a 0 versus a 1, or is it just we don't know?
We don't know.
Okay.
Actually, there are some field examples. There are many field examples generated by GAN, some people use GAN to generate physics, and they found that it has some hands, or it has 2 noses on the face. It's possible. There's no guarantee on that.
I know that in order to give it specific examples, you can have like embeddings for your noise. So the noise you give to the generator, you have like a certain set of noise that specifies what kind of output to generate. I know that that's how they fine tune it to say, hey, I want a generator that can do only 8.
Okay.
Oh, okay. That's a good idea. Yeah, that's a lot of like tuning tricks on GAN.
Just a following up comment. The Sexy paper that's conditional game. So basically, you have given an input and a noise random vector, you can generate based on that.
Yeah. So actually, I mean, most fantastic applications of GANs are in images. People found a lot of interesting applications on that, especially it's called stylish. You can move the face of one people to another person's face, and you got like money. Like if you search for the YouTube, you find like some fake Obama speech, and I mean, ordinary people cannot differentiate this is a fake speech. But it's just a fake speech. Obama never did such a speech. And yeah, I suggest you to search find examples online.
So why would you use a GAN for generation over a variational autoencoder? What are the benefits to using a GAN versus a VAE?
Use VAE.
Yeah.
VAE
Both of them generate.
VAE aims to project the high dimensional data into a low dimensional representation.
But you can also use it to generate.
Yeah, you can use that.
Right. So
Yeah, but I mean, from a theoretical point of view, I don't see any theoretical advantage of GAN over VAE.
Okay.
But I think it's just from practice. People like you can because VAE you can use a decoder to generate whatever. You can do actually low dimensional representations and say what does the decoder generate. But people found that's not very good. It's not as excellent as GANs.
Okay.
Right? Otherwise, I can use any dimensional reduction technique to do similar kind of things. You can even use k-means to do that. But people find k-means is far from satisfactory. K-means does not Gaussian mixture model.
Neither there are some comply with the use the age to master generation and the neural network as a discrete. So you combine the ranges of
Yeah.
and generate very high quality image.
Yeah, anyway, using GAN is really helpful right now. So if you put a paper as some kind of GAN, it might improve the 5% chance or 10% chance to get accepted. So here are a few applications like deepfake, style transfer, computation, whatever, many funny applications online. And now we have a wrap up. Like we have introduced I believe all the key techniques regarding the Bayesian neural nets. So what do you need to know? So first, what are the Bayesian neural nets? You should be able to write down the strong probability of your Bayesian neural net. So what's the key idea of that application? It's the fast optimization, right? We do not go through the detail of that application, but you should know what's the key idea of that. You do not need to manually derive that application because there are a lot of mature libraries on that, but you should know what's the idea of that. And what's the idea of stochastic optimization? How do we conduct variational inference for Bayesian neural nets? And what is the reparameterization trick? Also, what's the key idea of the space by back propagation, variational autoencoder, and GANs? And finally, and most importantly, you should be able to implement them with TensorFlow, PyTorch, or whatever neural network package. Now, okay, so. We have finished Bayesian neural nets. So now, in today's remaining lecture today, and also first half lecture on Thursday, we'll cover the last topic. It's called Gaussian process for regression. So you say, I mean, from modern point of view, it's very, very different. Another way to learn functions from data. It's purely probabilistic method. But finally, we'll see the striking connection between this Gaussian process and linear models, and also generalized linear models, and also the Bayesian neural nets. So here's the outline. So first, I'm going to introduce the idea of the Gaussian process regression. So what is Gaussian process prior, and then how do we conduct training and prediction? You see that if you use Gaussian process, the training prediction is really straightforward. and you're easy to obtain the analytical predictive distribution. And finally, we will prove the connection to Bayesian networks. So first, what is a Gaussian process regression? So first, we know that the key task for machine learning is to estimate a function of data, right? So giving you a set of training examples and a set of inputs and a corresponding set of the outputs, I want to estimate function of that. So we now that we're looking at Bayesian learning, probabilistic learning, right? So the key idea of Bayesian learning is that for everything I want to assign a prior. I want to assign a prior, then I assign data likelihood given the data, and then I combine the prior and the likelihood, calculate the posterior distribution of anything I'm interested in. So right now, I'm interested to estimate an unknown function from data. And natural question would be, how do we assign a prior over functions? That's kind of interesting question, right? So you can view like these different instances of functions, right? Each function is one-dimensional function, one-dimensional input function. Each function corresponds to one curve, right? So can we assign a prior over function such that a sample of the prior will be such kind of curve? That's the problem we want to discuss today. So from all the probabilistic models we have discussed so far, we know how to place a prior over several random variables. Right? So I have like m random variables, z1 to zm. I can assign a joint prior distribution over this m random variables, like multivariate Gaussian distribution or T distribution or Dirichlet prior, whatever. Then I want to ask, like, how do we extend this idea of the prior distribution to be the prior from functions? So the key idea is as follows. We're not gonna imagine functions as such kind of continuous curves. It's just for visualization. On the other hand, we can view function as a big table. So I have two columns in this table. The first column are the input of all possible input of the function. And second column are the corresponding function output. So you have the x1, x2, x3 to x infinity. And you have corresponding function values, fx1, fx2, fx3, under fx infinity, right? So now, if you want to assign a prior over functions, we're essentially assigning a prior over all possible function outputs, right? So basically, we view every possible function output as a random variable. And now we want to assign a joint prior distribution on all possible function outputs. That's the idea, right? And all possible function outputs actually comprise this, form this curve, right? That's the key idea. So we view each function output as a random variable. Now we want to place a prior over all the function outputs. But here I want you guys to forgive my. This is not very rigorous. Why? Because many functions say their input is like continuous and infinite uncountable. That means I cannot use integer to index their inputs. So, but here just for illustration, just conceptually to illustrate that, because I cannot use index to. I cannot use integer to index all the possible inputs, because this all possible set of inputs is infinite, uncountable. If you have taken a discrete mathematical class, you should know what I'm saying. So rigorously speaking, we should not use integers to index the input. But anyway, the collection of all possible outputs are just a collection of random variables, right? In theory, we should be able to assign prior over them, although this collection is infinite, uncountable, right? So that means we need to assign prior over the collection of all the function outputs which are infinite and uncountable? And is it doable? The answer is yes, and it's grounded on a very elegant and rigorous probability theory. And such a part is called a random process. So very informally, you can view random process as a collection of random variables. And usually, when we talk about finite number of random variables, we won't talk about in terms of random process. When we talk about random process, we really refer to a collection of infinite random variables. But here I want to give you a rigorous definition of a random process, such that we can give a more, essential view rather than some kind of weak concept of that. So what is random process? If you still have impression about definition of random variable at the very beginning of this semester, you can start to do the final review a little bit earlier. So what is random variable? So random variable is not random, it's not a variable. So random variable is essentially a function or a mapping. Right? It's mapping from your sample space, which consists of all possible random experiments outcome, right, to some variable space, and we do not need to talk about what is variable space, but you can view it as like some real value domain, right? So like you can do many random experiments, like I toss a coin, right? Then my sample space will just be head or tail, right? Now I want to construct a random variable which map head or tail to some real value, say 0, 1, or -1, +1, or 0.5, 1.5, whatever you want. Then we call this mapping as a random variable. And because this mapping associates a real value with each random experiment's outcome, we can see some randomness of the real value. And then we can deal with all kinds of real value in the real value space because that's more convenient, that's more rigorous, right? That's the motivation to define the so-called random variable. And when we talk about random variables, we usually refer to the image of the random variable. The domain it maps to, but conceptually it's just a mapping. So what is random process? Random process is essentially an extension of random variable. It's also mapping, but it's a mapping not only between the experimental outcome space, but also between an input t. So it's a function of an input t and the experimental outcome. And map this pair of the input and experimental outcome to typically say a real domain. So originally this t is referred to like time, but actually t can be actual input, like actually functions input. That's fine. So now you can view like random process as a function of two parameters, right? One is some input t, the other is the experimental random experiments outcome, right? Then you can have two views of your random process. First, if I'm gonna fix the input, then your xt omega is just mapping from omega, from the experimental outcome to some real value. So then your xt omega becomes a random variable, right? Because you have fixed t. But another more interesting view is that what if you fix omega? You fix omega means you fix the experimental outcome. Now you're free to vary the input t. Then xt omega is essentially a function that determines the function of t. What does it mean? It just means when you fix omega, each omega from experimental outcome maps to a function. Your different omega will maps to different functions. So you can imagine like the original random variable definition are like each experimental outcome will correspond to a real value. Like head corresponds to 1, and tail corresponds to 0, right? But now in the random process, each experimental outcome corresponds to a function. Like head may correspond to sine function. Tail corresponds to a cosine function. Or third outcome may correspond to, say, whatever other functions, right? Square, any function one, right? So we can take a look at this example, right? So here are the random process when we take 3 different outcomes, omega 1, omega 2, omega 3, it will correspond to 3 deterministic functions, right? Does it make sense?
So every time I call x of t w1, I'm going to get that, whatever that function is, that thing.
Yeah.
And it won't, if I start at the same t, it'll look the same. I guess. That's the point.
You mean this is you fix omega 1. Like you vary t, you get different value of x t omega.
Okay.
So it's a function. Right? Now if you switch omega 1 to omega 2, the function becomes this. Right?
Okay.
When you vary t, you have different values like this. Right? So actually mapping from the experimental outcome to a function rather than a number. This is the definition of random process. Does it make sense? At the same time, if you look at along this way, right? If you fix t, say every x here, you fix a specific t. Then different omega 1, say omega 1 will correspond to this value, omega 2 will correspond to this value, and omega 3 correspond to this value. This is a random variable because different omega will correspond to different numbers. It's random variable. Again, if you switch to another t2, then the 3 xt2 omega 1, xt2 omega 2, and xt2 omega 3 will correspond to 3 other random variables values. But we're more interested in this one, right? Because we will, from definition of random process, we can see that we're actually mapping your experimental outcome, which are random, to some deterministic function. Because the function associated with the outcome for some random experiments, that means the function must have some randomness. I can assign some probability on that. That's the validity of assigning a prior old functions. Does it make sense? Is everyone comfortable? Okay. So now, this is a general definition of random process, right? But the question is that, for different types of random process, those function curves will vary, right? It must follow some properties or constraint, whatever, right? So now we're going to ask, now what process are we going to use to sample function? And because we're talking about the Gaussian process part, obviously we're using Gaussian process, a specific type of random process. And also there are other random processes like T process. You can use that to sample functions as well. And also Dirichlet process. That function generated by some kind of a discrete function. It's not a continuous function. So what is Gaussian process? If I'm taken random process course before, Gaussian process might be the simplest random process. So if a random process has every finite collection of the random variables followed in multivariate Gaussian distribution, this process is called Gaussian process. So basically, remember, the process can be considered as a collection of infinite uncountable random variables, right? If I pick up an arbitrary subset of random variables and they jointly follow a Gaussian distribution, then we can claim this process is following a Gaussian process. And similarly, like T process just means like arbitrary finite collection of the random variables in the T process follows a student T distribution, a multivariate T distribution. So specifically, how do we parameterize this finite multivariate Gaussian distribution? So given any finite set of inputs, so you have big n inputs, right, x1 to xn, then the corresponding function values will be fx1 to fxn, right? So remember the definition of the random process, omega t, right? So when you have a fixed t, you correspond to random variable. Now we have n fixed inputs, right? So I have n random variables, which are fx1 to fxn. Don't confuse by this notation, just use some garbage notation, right? So Gaussian process simply requires that for arbitrary such a set of function values, the outputs of the functions, they follow a multivariate Gaussian distribution with covariance to be a kernel matrix. So what is kernel matrix? Kernel matrix is a matrix computed by a kernel function. Okay? So each element in this kernel matrix is a kernel function of two corresponding inputs. Say, in this kernel matrix, the element at ith row and the jth column is just the kernel function of ith input and jth input. Say, the first element, right? First row and the first column. So the element at this covariance is kernel function of x1, right? And the first row and second column, the element is kernel function of x1, x2. And nth row and second column, the element is kernel function of xn, x2. And you just expand it and to compute the full kernel matrix and use this kernel matrix as the covariance. That's how we define the multivariate Gaussian distribution for a specific Gaussian process.
Why is the mean selected to be 0?
Actually, it's not necessary to be 0.
Okay.
You can use, like, I mean, in practice, most models simply do 0.
Mm-hmm.
But in theory, you can put it as another function. Like it's called mean function, and you can evaluate at this endpoints and mx1 to mxn as its mean. That's fine. But most cases just simply use 0. Any questions so far? This is the definition. So in view of that, a Gaussian process is actually defined or determined by a kernel function, right? Because I want any finite collection of the elements in this process follows a multivariate Gaussian distribution, and the covariance is determined by the kernel function. The covariance is computed by the kernel matrix over the corresponding inputs. Right? That's the idea. So what does kernel function do? Kernel function actually measures the similarity of two inputs. So here, I give you one commute to the kernel function is called RBF kernel. So the computation is simply exp to the power of minus inverse of tau, which is some parameter, right? And the square norm of difference between x and xg. So you can see the closer x and xg, the larger the kernel function, right? The closer is different. The closer x and xj, the square norm difference is smaller, right? Then you take minus, it gets larger, right? And take exp, it gets larger. So the closer, or the more similar the two inputs, the larger the kernel function. So what does that mean? What does that mean? Remember, our function output, any set of function outputs, right, are sampled from some zero mean, and the covariance matrix is actually the pairwise similarities between the inputs, right? Because I'm calculating the kernel functions between every pair of the inputs. So this essentially implies that the closer the inputs, the more correlated the function outputs. This is what the multivariate Gaussian distribution defines, right? The larger the elements in the covariance, the larger the elements in the covariance matrix, right? The larger the correlations between the corresponding outputs, right? Does it make sense? I mean, off diagonal element. The diagonal element just means the variance, right? But off diagonal means just say this is at 1, 2, right? This one first row, the second column, this element here. The larger this element, it just indicates the larger the correlated y1, y2 are, right? So basically it means that if your inputs are very similar, then your output should be highly correlated. Essentially, describes the function smoothness in a probabilistic context. Why? If you look at function curves, right? So we know that according to the smoothness, the closer the two inputs, the closer the corresponding function output, right? From a probabilistic context, we can now say, okay, they must be exactly the same. We can only say they are higher, more correlated. That's the idea. Because we view every function output as a random variable. We cannot say, oh, two random variables is exactly the same. We can only say, okay, the two random variables are higher correlated when their inputs are close, or more similar, right? Does it make sense? Does it make sense? This is a very smart way because you can say, well, assign this prior, we do not assume any form of your function. We don't assume it's a linear function or square function or cubic function, exponential function, whatever. Right? I just require, okay, if your function's inputs are close enough according to the kernel function definition, then your output should be highly correlated. That's it. All the other things are inferred from data. And then things become how do we define the kernel function. Right? The kernel function ways to measure similarity, but there are many ways to measure similarity. So actually, there are numerous ways to define a kernel function, and different kernel functions define different ways to measure similarity. So although in theory we can assign some prior over the whole collection of function outputs, namely the random process, but in practice, we never need to sample the whole function because the training data are always finite. Remember when we construct a probabilistic model, we're going to give some prior, and then given the prior, we generate the data, right? But now data is finite, right? Why do we bother to use prior to sample an infinite number of the random variables? It's not necessary. So in practice, we never need to sample the whole function. So now let us look at what do we construct a Gaussian process regression model. So suppose we're given a set of training data. So we have big N input and big N output, right? And how do we construct our probabilistic model to sample the data? So first, we're going to sample the function values as the input. We're not going to sample the whole function. Because even given the whole function, we only need to sample the likelihood of the discrete, finite discrete function output, right? So actually, we do not need to sample the whole function. We just sample the corresponding n function values. What's the distribution of these n functions values? Yeah, I heard that, right? According to Gaussian process prior definition, any finite subset of function values must follow a multivariate Gaussian distribution. That means you can just assign a multivariate Gaussian distribution over this n function values, right? And the covariance is the kernel matrix over this n equals. And then, given the function values, we're going to sample the observed output. For the regression test, which is what we are talking about now, right? So for the regression test, we use continuous output. And we usually use Gaussian likelihood. We assume the observations are corrupted by some random noise. So that's the same as we use for linear regression. Then we assume given y, given f, y are sampled from a Gaussian distribution with covariance to be some sigma square I. So the sigma square is noise variance. So now we can write down the joint probability, right? We have the prior for the latent function values over the n inputs. Then given latent function values, for this prior, we sample the observed function outputs. So if you write down the graphical model, it's straightforward. Right? You have function values over this n inputs of sample first from this multivariate Gaussian distribution. And then given the function values, your sample the observed corrupted observations. That's it. Any questions so far?
So you make the assumption that the noise assumption so that you can model it as a Gaussian?
Yes.
Okay.
You can change the assumption. Definitely. You can change the assumption to be used other, like I have seen some paper like use T likelihood, student T likelihood to model how we sample the observed Y to account for like more losses. And if your observation is not continuous, like it's binary, of course you need to switch to say Bernoulli likelihood. Any other question? So you can see essentially, I mean the concept is really amazing, but the modeling is really simple. It's just the prior. The prior conceptually is a function prior, but we only look at this the finite version, which corresponds to the multivariate Gaussian distribution. And what we need is to compute the covariance, compute the kernel matrix, use that as a covariance matrix. And then you can see in the Gaussian regression, I mean Gaussian process regression, you have two Gaussian multiplying together, right? So we know from this likelihood we can write the observed output y equals to f plus some noise, right? So it's not some random noise, right? So this random noise can be seen as a sample from some Gaussian distribution with a sigma square as noise variance, right? And this f is our latent function values. So again, linear combination of independent Gaussian random variables is still Gaussian random variables, right? You just simply compute the expectation and covariance. Right? Expectation is simply 0 because the prior of f is simply 0. And prior of the noise is simply 0. The covariance is just that as the covariances of these two Gaussian random variables, right? And then you can obtain the marginal distribution of the observed output, which is another Gaussian. And the covariance will be the kernel matrix plus a noise variance. That's it. So up to now, any question?
That final distribution is over all outputs y, right?
Yeah.
Okay.
It's observed output. So now let us look at that, right? So we have a saying like the kernel function actually takes the most important role to construct a Gaussian process model, right? So as we mentioned before, the Gaussian process requires that for actually finite set of inputs, the function values must follow a multivariate Gaussian distribution that covariance is a kernel matrix. That implies that this kernel matrix must be a positive semi-definite. That's our requirement for kernel function. for any finite number of inputs, the corresponding kernel matrix must be a semi-positive definite. This is called the Mercer's condition. This is a discrete version of Mercer's condition. It's not continuous version. So here I give you kernel examples. Like linear kernel, simply inner product. I have x and z, polynomial kernel. You do the inner product, you take the power of d, and polynomial kernel up to some degree. RBF kernel, periodic kernel, matrix kernel. And even right now, people are trying to use like deep neural nets to construct kernels called deep kernel. If you're interested, you can search for kernel cookbook in the web. The pop-up web page will give you all kinds of different kernels. So, but here I want to mention an important, essence of kernel function. What does a kernel function do, right? So each kernel function, each valid kernel function which satisfies the Mercer's condition, corresponds to a possibly high-dimensional nonlinear feature mapping. And the kernel function itself is essentially an inner product of the mapped feature vectors. So each kernel function essentially associates such a feature mapping. So this feature mapping maps the original feature vector to some new feature vector. So you can see it's RK maps to RD, right? And usually D is far larger than K, means that this mapped feature vector is very high dimensional. And oftentimes D is infinite, means that okay, your mapped feature vector is infinite dimensional. And the kernel function is equivalent to do the feature mapping first, and then do the inner product second. So from another perspective, kernel function is a cheap way to compute the inner product of the high-dimensional feature vectors. Because if you want to do the explicit feature mapping, you can imagine, especially if D equals infinite, essentially you won't be able to compute. How do you compute an infinite dimensional vector, right? You won't be able to compute, and you won't be able to compute their inner product. But doing kernel function, you're implicitly doing this, right? And the computation is much cheaper. So this way is called kernel tree. It's very classical tree in machine learning. And actually, the branch of machine learning is called kernel learning. It's based on, the center topics around this kernel tree, and also the representation about those feature mapping and their expressiveness, etc. But what do we see from this inner product, right? So, because kernel function can be viewed as inner product of the mapped feature vectors, we actually, from this, we can find out another view of Gaussian process regression model, namely a linear model, a generalized linear model. Thus, the very first type of models we discussed in the class, right? So how do we view it, right? Again, we use the same setting. Assume we have like n training examples, x1 to xn are training inputs, y1 to yn are training outputs, right? So now I construct a linear model. How do I construct a linear model? I'm going to first sample a weight vector. The length of this weight vector, or dimension of this weight vector, matches the length of the mapped feature vector psi. So it could be infinite dimensional. Let's just put aside practicability. Let's just view it in theory, right? Let's just assume like, okay, even psi is infinite dimensional. I'm able to sample such a weight vector from an infinite dimensional Gaussian, standard Gaussian. And then for each example, xn and yn, I sample yn from this Gaussian distribution, where the mean is inner product between the weight vector and the mapped feature vector. And the variance is sigma squared. So this is typical Bayesian linear regression model, right? Except that we're now introducing a nonlinear feature mapping. This is consistent with our general definition of the linear models, right? And now we can write down the drawn probability of this model. Right? So the drawn probability will be the prior of W, right? Then multiplying with the likelihood over each string example, which is a Gaussian likelihood. I just copy here, right? W transpose psi Sn sigma square I, right? Does it make sense? Okay. So this is drawing probability. W y given x, right? So this part can be written, I mean, for convenience, we have done that before. We can written as a Gaussian distribution as well, right? And we can written as like phi x times w and sigma square I, right? This one is a matrix. It's called design matrix. You still have an impression on that. So each row corresponds to a map to feature vector. So if you write it down as phi x, it will be the first row will be psi x1 transpose, right? Second row will be psi x2 transpose. You just enumerate all possible rows. The last row will be psi xn transpose, right? So you can imagine the size of this design matrix is n by d, right? D is the dimension of the map to feature vector, right? And W is d-dimensional. So you multiply psi with phi with W, you end up with mean for each Gaussian likelihood, right? So just just a matrix representation in this product, right? And your covariance is a diagonal matrix in sigma square I, right? Then, if you write down, expand the prior for the W, that will be the standard Gaussian, right? So this is our drawn distribution. No problem, right? So now let's try to marginalize our W. See what we can get, right? So how do we marginalize our W? So first, from this likelihood, we know our Y. I mean, Y consists of all the outputs. It's a vector, right? Can be written as this design matrix times W plus Gaussian noise on the variable epsilon, right? Epsilon samples from this Gaussian distribution with covariance with sigma square I, right? So now this is W is Gaussian, and Gaussian noise, of course, is Gaussian. It's a linear combination of two independent Gaussian variables. So Y must be the marginal distribution of Y must be Gaussian as well. How can we compute the marginal distribution of Y? First, the mean of Y is simply 0, right? And the covariance, how can we compute the covariance of Y? You have done the homework before, right? So it's simply phi x design matrix is constant with W, right? So it's actually phi x then times covariance of W times phi x transpose plus the covariance for epsilon, which is sigma square I, right? Then what is the covariance of W? I, right? Because W is somewhat from the standard Gaussian, right? So that means the covariance of Y is simply the outer product of the design matrix plus this noise variance, noise covariance sigma I, right? Now let us look at what is the outer product of design matrix. So this is our design matrix. If you multiply this design matrix with its inner product, with its transpose, so phi x transpose will be psi x1, psi xn, right? So you can view it as like a column block matrix multiplying with a row block matrix, right? So each element will simply the inner product between each row and each column here. Right? So that means your phi x transpose will be something like this: phi x1 transpose phi x1, phi x2, phi x1 transpose psi x2, blah blah blah, until psi x until psi x1 transpose psi xn, right? And similarly, second row will be psi x2 transpose psi x1, psi x2 transpose psi x2, psi x2 transpose until psi xn, right? So from our definition, each inner product will be a kernel function of the corresponding two inputs, right? So this output product essentially is a kernel matrix, KXX, right? Then we reduce to the Gaussian process regression, right? That means from this point of view, Gaussian process regression is essentially to first do some nonlinear feature mapping. Although this nonlinear feature mapping might be infinite dimensional, but then I apply a Bayesian regression model. Then I marginalize out the feature weights. I got the same marginal probability. So these are two views of Gaussian process. First is from functional space view. You can view as sample functions bar, and then you sample the discrete function outputs, right? And second is that just simply view it as a special type of generalized linear model. So here's this definition of Gaussian process regression. Now let us look at the training and prediction. So we have written down the joint probability of our Gaussian process model if we include the latent function values, right? We first sample the latent function value from a multivariate Gaussian distribution, then use Gaussian likelihood and Gaussian distribution, Gaussian noise model to sample the observed outputs y, right? Then what kind of training algorithm can we use to train this? F is latent random variables, right? And we have noise variance and also kernel parameters to estimate. So it's a typical scenario for YAM algorithm. You can apply YAM algorithm to jointly estimate the posterior distribution of your function values and also the hyperparameter statement, right? But this is not, the YAM algorithm is not often used in Gaussian process training. So in practice, we often do type 2 MLE. So if you still have an impression what is type 2 MLE, you just marginalize all the latent random variables. And I got the marginal distribution of the observations resolve the latent function values, right? Then I maximize this large marginal distribution with respect to the noise variance and kernel parameters, which we refer to them as the hyperparameters theta. Any questions so far? It's pretty straightforward. And then the prediction is even straightforward. Now we can use our knowledge about the multivariate Gaussian distribution. Now that we are tortured by that before, right? But now we can see its usage. So given a test input x star, how do we predict the function output f(x star)? So remember, according to the definition of Gaussian process, right? Any subset of the output must follow a multivariate Gaussian distribution. That means your test output and the training output must jointly follow a multivariate Gaussian distribution. And then you can and means into 0. And covariance is kind of kernel matrix. But here Y is some noisy output. You should add some noise parameters here. All the output the same. So this is actually a block matrix of the whole kernel matrix over X star and X. So you have KX X star corresponding to this test output, right? This cross is called cross kernel function. From calculate X star, the kernel function between X star each input in the training input, right? So this is transpose of this cross kernel, right? This part is for the covariance matrix for the noisy output. And now I have constructed this multivariate Gaussian distribution to compute the posterior distribution, which is a conditional Gaussian distribution. So what is the distribution of the test output given the training output? From this John Gaussian, we can immediately use conditional Gaussian to obtain the posterior distribution. Or that's not posterior distribution, essentially a predictive distribution. So this is predictive mean, this is predictive variance, and I have written down this formula for 1,000 times so I can know effortlessly write down the mean and the variance. Although it looks like it looks lengthy. So finally, I'll give you the view of the prior functions and posterior functions. If you use Gaussian process prior to sample the function, you say, okay, the range of these functions are large, right? It can be the function can be this, can be all kinds of weird functions. Right? But after giving the training examples, you do the prediction. You can use predictive distribution to sample the functions. Why? Because for any input X star, you can sample the corresponding function value, right? If you want to get such a kind of curve, you just give a set of densely distributed inputs, right? And then you sample the corresponding function value from this predictive distribution. Then you connect all the outputs, you get a function curve, right? That's how these posterior functions are drawn. You can see that those shaded region just represents the variance, the predictive variance. You can see that for those parts, like variance is very close, but it's not necessary to be 0. Are the points for the training data. So again, when in our posterior function, when we cross the training data, the predictive variance is quite small. That's reasonable. But for the regions that far away from the training data, I still have like a relatively large variance on that. And you can imagine that in my posterior Gaussian process, those are all possible functions I have in my hand. Any question? Okay, great. So let's stop here, and I'll see you on Thursday.
Wow.